We've now looked at sp3, sp2 and sp hybridization and associated pi bonding when we look at alkenes and alkynes. So I thought it may be a good idea to look at another molecule. This time we're going to look at carbon dioxide and try and work out how the carbon and two oxygens are bonded together. So let's remind ourselves of the bonding in carbon dioxide. We obviously have carbon with two double bonds, one double bond to oxygen A and one double bond to oxygen B. I've just labelled those two oxygens with A and B, so it will give us an easier way to tell their bonding apart a little bit later on. And so the bonding between oxygen A and carbon. So this will consist of a sigma and a pi bond, and between carbon and oxygen B will also consist of a sigma and a pi bond. So that means that carbon forms two sigma and two pi bonds. So that's going to be sp hybridized. To leave two p orbitals over to pi bond. Oxygen is going to be sp2 hybridized because remember oxygen has also got two lone pairs which it will need to locate in orbitals as well. So it will be sp2, both will be sp2, and that will leave one p orbital over to pi bond with the carbon. One of these hybrid orbitals will be used to form the sigma bonds, and the other two will be used to form the have the lone pairs. So that's a little summary there. So we can see that we have got oxygen A, sp2 hybrid orbitals, carbon with sp hybrid orbitals, and oxygen B again with sp2 hybrid orbitals. So let's have a look and see how these orbitals are formed. So carbon you'll be familiar with, I'm sure. Carbon is going to use the 2s and 2px to form the sp hybrid orbitals, which will have two lobes along the x-axis. So here are my two sp hybrid orbitals with the lobes along the x-axis, and that leaves us our py and our pz p orbitals to pi bond. We'll have a look at oxygen now, so let's consider oxygen A first of all. So I'm sure you remember oxygen has got 6 electrons in the outer shell. So the 2s has going to have 2 electrons in, along with the 2px. Now these electrons will be mixed around to form sp2 hybrid orbitals, which will be made up of our s, our px, and our py in this case, which means our lobes will be in the xy plane, because we haven't used any of the we haven't used the z pz orbital at all. So they're purely consisted in this plane, which will be going in towards the screen. And that means that these two hybrid orbitals will be used to have the lone pairs, and this one will be used to bond. And our 2pz we will look at later when we look at the pi bonding. Oxygen B, again, same initial electronic configuration, but we'll use slightly different orbitals to form the sp2 hybrid orbitals. So oxygen B is actually going to use the pz and as getting px and the 2s. That leaves the py over to pi bond with the carbon. So our hybrid orbitals, their lobes are all in the x, they're all going to be in the xz plane, because we haven't used the py orbital. This will become important a little bit later on. So let's look at the sigma bonding. first of all. I've just popped carbon up there, and carbon's sp hybrid orbitals, for which you remember carbon used the 2s and the 2px, so the lobes of the orbitals are hybrid orbitals are along the x-axis. The red circle there will become useful hopefully a little bit later on for you, but it's just to illustrate the xy plane at the moment. So that sort of like circle, donut if you like, is in the xy plane. So we introduce oxygen A now. Oxygen A, you remember, has formed sp2 hybrid orbitals using the 2s, 2px and the 2py orbitals. So the lobes of these orbitals are in the xy plane because we have not used the pz orbital. So this red donut that you can see there is in the same plane as the lobes of oxygen A hybrid orbitals. And now we introduce oxygen B into the game. So oxygen B again has got sp2 hybrid orbitals, but rather than using the py, has used the pz. So its lobes are in the xz plane. So they are perpendicular to the donut. So the donut is now showing you the xz plane, which the lobes of the hybrid orbitals are in. I've also added in the angle between the lobes of the orbitals there, the hybrid orbitals there. For oxygen, it's with sp2 hybrids, it's 120 degrees, and for carbon with sp hybrid orbitals, it's 180 degrees. So let's try and put our three atoms together now. So in the middle there, the one that you can see is going to be our carbon atom with the two lobes coming out of that donut. Again, the donut is just there to help you with the 3D visualization. So you've got those two lobes of the sp hybrid orbitals. So let's now look at oxygen A. So oxygen A, when oxygen bonds with carbon, those lobes of the sp2 hybrid orbitals overlap, and we have our sigma bond, which we are showing here with our dot and cross to represent that's a bond, and our lone pairs are here and here. And now we can consider oxygen B. So we bring in oxygen B, so very similar in terms of having our sigma bond here. However, now the lobes of the lone pairs are in a different plane. Remember that the donut now that we are showing, this donut is in the xz plane. So the lobes are here and here are in the plane of the screen, whereas the lobes of the oxygen A atom, those lobes are coming out towards you and going in to the screen. So this just summarises our sigma framework and our hybrid orbitals and sigma bonds for oxygen A, carbon and oxygen B, to just show you how those electrons are held in the bonds or in the hybrid orbitals. So we can now start thinking about how the pi bonding works. And you remember that in our pi bonding, we have got use of different p orbitals for oxygen A and oxygen B. So oxygen A hasn't used the pz and oxygen B hasn't used the py. So I've just shown those orbitals there and we will now come in with our carbon. So let's bring in carbon, and remember carbon has not used the 2pz or the 2py. So it would make sense for the carbon 2pz to bond with oxygen A's 2pz, and oxygen's B2py to bond with carbon's 2py orbital. So here I've just shown the overlap between oxygen A and carbon using the 2pz orbital. And this slide shows the overlap between the 2py orbitals and the pi bonding between carbon and oxygen B. And on the next slide, brace yourself, we can bring it all together. This shows how the bonding all comes together. So we have our lone pairs are held here, 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 and here. We then have our two sigma bonds here and here between the carbon and oxygen, and we have a pi bond here between carbon and oxygen A, and we have another pi bond here between carbon and oxygen B, which of course leads us back to our original diagram of our double bonds between carbon and oxygen. But the key thing to know is you have to be wary of which orbitals you use in the hybridization to make sure you have the right ones free to form the pi bonds to overlap with the other atoms' available orbitals. So I hope that was a nice introduction or extension to bonding with hybrid orbitals using carbon dioxide. And we have one more video coming up in this series where we will look at how we can use d orbitals in hybrid orbitals. As ever, you can download this presentation from the website as a PDF file. Just follow the link and you'll be able to click on the extension material and download this.